on quantum computing. I'm doing quantum computing, and from last time, I was working on the knowledge gap engine, where I was using concepts in quantum computing to try and create an algorithm that can run on classical computers. That's what they call the knowledge gap engine. And I was using some concepts in quantum computing when working on it, what we see as superposition, entanglement, uh, interference, probabilities. So I'm using concepts in quantum computing to try and work on this system. So what this system does is, as a reminder, since we have talked about it last time, but what the system does is that it takes all the discoveries that have happened from history. It takes actual discoveries. I'm using Wikipedia right now as my source of information. So it takes all the discoveries that have happened, and using quantum computing, it looks for hidden connections between a certain nodes, certain discoveries, maybe things that we may have missed that that could be useful. So what I'm doing is like an accelerated form of research. I don't know if you're hearing me. If you're hearing me, just put a thumbs up so that I know that you guys are hearing. Yeah, all
We
right.
can hear.
All right. So I'm doing something of an accelerated research. Where I'm trying to boost in how fast we can make our research, how fast we can make our studies. And one of the things that I like about quantum computers or quantum computing is that it works faster. It boosts, like it does a lot of heavy computation. But since I do not have access to quantum computers, I don't know if I mentioned last time, but quantum computers are not like these classical computers. They're usually very big in size, and they need to be in a special environments because they're very sensitive to temperature, to vibrations. So what I did was, as I make research on quantum computing, I'm going to be using just the concepts and try to simulate or to force an algorithm to behave as if it was in a quantum computer. So what you're seeing right now in your screens is I'm trying to visualize the research I'm making, because most of the things I was working on was a lot of theories, and the practical was happening in the background. So I was using a print or SQL queries to try and do what I was working on. So I've been working recently a lot on trying to make it more visual, whereby I can show, maybe I can see what I'm actually doing. I can maybe put the discoveries, I put the nodes that are connected, and then I try to run some algorithms and see what other connections are between the nodes. Let me try to increase the brightness. I don't know if it's brightness. Anyways, I've tried to increase. I don't know if to increase your side. So, so the nodes, the gray nodes are the discoveries. Right now, I'm running a physics. I'm trying to run a physics discovery. The discoveries that happen in physics between 1800 to 1900. The gray nodes are the discoveries that happened, and then they are connected. There is some sort of connections between each node, and then the nodes are placed based on time. So from left to right, they're the earliest to the latest. So what this system is trying to do, it is trying to show me what discoveries are connected as we know them, and what potential connections, what alternatives that these discoveries could have had, like which other connections could they have led, so that they lead to to the present day that as we know it. That's what I'm trying to do. The algorithms I'm using to try and find out the connections between these nodes. I'm using three algorithms. I'm using three different algorithms. The first algorithm I'm using is let me check it out. Let me check it out. So the first algorithm I'm using is the Jaccard coefficient. So the Jaccard coefficient algorithm, in simple terms, it looks at two nodes and it sees if those nodes have identical neighbors. So if we have a node on a node A and we have a node B, it looks at what fraction of the neighbors do they have in common. So this Jaccard coefficient algorithm says that if they all have identical neighbors, it gives them a score of 1. If they have no identical neighbors, that means it gives them a score of 0. This is one of the algorithm I'm using. Another algorithm is called the Adamic Adar Index. For this one, what it does, it looks at what maybe if they do they have something in common, but do they have specific neighbors in common? So, for example, if A has a neighbor which is rare, which is only being shared by A, does B also share these specific characteristics? So it's looking for rare cases or rare neighbors, and it looks for who is sharing that rare neighbor. So if A has is sharing, it has as a special neighbor. There's also B shared that has a connection to that special neighbor. And if yes, it gives this connection a high chance of happening. So it's quasi. If they don't share that rare neighbor, then it gives them a low score. Then the third algorithm is called the preferential attachment. This one is used to measure how connected are these two nodes. It checks for the product of their degrees. It checks the degrees, how connected are these two nodes? Maybe are they close? Are they far apart from each other? These are the three algorithms I'm using. I remember in the past I was asked, why don't I use AI to make this? Why don't I use a language model to run this? And actually, I'm using AI, just that I'm using it in a different way. Because when people say AI today, they usually mean deep learning, neural networks trained on large data sets. These language models that are trained on to look for patterns. So when this system uses a symbolic AI, an AI that is structured, reasoning based on some mathematical rules, the Jaccard, Adamic, Adar, and preferential attachments are the algorithms that I talked about earlier. They are derived from graph theory. They are not learned. They are more of defined. They are a form of AI. Um, there is how they are connected, that they're not based on patterns that already exist. That's one of the reason I'm not using the AI as we know it. I'm not using this AI that is trained on already existing data, because that one will also have bias when trying to find connection between the nodes. Yet I'm trying to look for something that won't be biased or won't be affected. It's already existing, because as we do research, we're trying to find things that not that do not exist, they exist, but maybe we ignored, or that we didn't try to study further. So that's the major point of research. So with this approach I'm using of not using the traditional AI as we know it, is I'm trying to make this system, this algorithm, to be as less biased as possible. Instead of having already known patterns, it uses defined rules, defined mathematical rules, and it tries to find connections between patterns. And again, it scores them it scores these research, the results it finds out, it scores them based on probabilities. It doesn't find the wrong or correct connections, but it finds the most which has the most probability of being correct, or the one which comes close to being true. And then based on that, the measurement is not the scientist. So after I've gained these results, after I have these nodes, these different results, so it is now the scientists to measure them to see which one which one is more likely to be true. So it's the researcher now to go and find out. So this algorithm helps you speed up your research, your studies. Then when you find when it scores you, you get the one which has the highest score, and then you go and set the it. And then as you measure, all the probabilities collapse to one single answer, which is the main concept in quantum computing, whereby when we measure something, it collapses into one answer. So maybe we shall go through how this system works. Because I have to make some more. I have to work on it further, and then maybe next time we shall be able to go through it and see how it works, how you can use it for research, what are its pros and cons. But for today, yeah, this is what I'm working on. I'm trying to visualize what I'm doing, integrating some stuffs, trying some stuffs, and hopefully it can be helpful. Yeah, thank you. Well, if you have questions, let me know. Well, I'll finish. I'll finish. I am just passing through them.
Thank you so much, Milton. I'll not be able to share today evening, possibly next week. Thank you.